Tell me, my Tell me,
the people where they locked up.
Kutima, apa edutare? Da.
Okay, so I think it's time to start. 8 minutes after 1, so I think it's time to start. Anybody that is not able to join the class will actually watch the video, so we can just start so that we don't delay people that are working, because some people are working and they have to just come and join the class. Okay, so let's just start. Okay, let's confirm we can see my slide.
Yeah, we can see your
slide. All right, thank you very much. Okay, so once again, welcome to our day 2 for our offshore production DCS simulation and operations training. Okay, so at day 1, we already introduced the course, and I believe everybody understand why we are here. Okay, so for day 2, we are going to go a little bit into DCS system, and also trying to make us understand why we need to have our DCS. So we'll have 2 modules for this course. The first one is introduction to DCS in offshore facility. Okay, then the second one, we're going to look at the HMI design and the process visualization. So that is what we're going to do in this course. Okay, so let me take out. Yes. Sorry, something is blocking my screen. I take this off. Nice. Okay. Okay, please, let's continue. Something was blocking my screen, so we can continue now. All right, so we are talking about DCS simulator in this is our module 3, right? Now, the DCS simulator, we all know, is applicable to all facilities, including chemical plants, including ethanol plants, including refineries, gas plants, offshore, and different facilities. As long as we have equipment involved, and then we have automation, then we have a DCS that is going to be there. Okay, so either we have DCS, we have PLC, or we have a SCADA. So we are going to look at the DCS aspects. Although somebody asked a question about difference between DCS and then the SCADA, so we're also going to incorporate that, and then we'll talk about the difference and what the places where we can have a DCS or a PLC or a SCADA. Okay, so this is the environment of a DCS. And if you've worked in any facility before, you know that this is the arrangement. This is the way DCS control room is arranged. Okay, now this differs from different companies, right? Now, a company like ABB, we have the arrangements in a different way. While a company like Emerson, Allen Bradley, let's say Supcom, there's a new company called Supcom from China.
We can't see your screen again, sir.
A company called Supcom from China. And
so the screen is blank. The screen is blank.
Are you serious? Just hold on.
Yes, sir. We are just seeing you. I'm seeing nothing.
Hold on. Can you see it now?
No, we are just seeing you. We are not seeing your screen.
No.
Screen is not sharing.
Hold on.
Your network today will be very slow.
Please, can we see it now?
Yeah, I can see your screen now.
Yes.
I can see it now.
Okay.
Yes,
I can
the
see you
screen
now.
is seen now. Thank you.
All right, sorry about that. Okay, so this is the DCS I'm talking about, okay? So every company has an arrangement like this for their DCS. Now, like I mentioned, companies like gas plants, refineries, any company that has automation equipment, and they have to be automated, they need a control room and the DCS to handle all the monitoring and optimization, okay? So this is what you see if you get into a control room. Now, for the students that have not heard the word DCS before, DCS stands for Distributed Control System. Okay, so we'll talk about what this means later on, but just understand that this is how the DCS looks like. Now, early 1960s, or let's say below 1970s, there was nothing like a DCS system, right? So from 1970s and above, that's when we start having DCS system, and they all graduated at different levels. Like the automation level was increased from year to year until we get to what we have here today. Okay, so before they were using pneumatic systems for their controls, but right now everything has been advanced. Okay. So like I mentioned, distributed control systems means DCS means distributed control system. Now, it is a primary automation platform used to monitor, control, and optimize. Okay, so the DCS control system, the DCS or the control room, is where personnel, observe and monitor everything that is going on in a plant. Now, for offshore, it's exactly the same thing. Now, you have to monitor your production, monitor the parameters from the DCS, like your temperature, your pressure, your flow rates. Now, these are the important things that you monitor from the DCS. So, unlike the manual or localized control systems, like I mentioned before, in those days, they use their senses, their ears, and every other thing to try to visualize what is going on. You can even get to the level where they use ear to put on a pipe to listen if there is flow or something like that. Okay, that was before the advent of the DCS system. So currently now we have a centralized system that try to distribute all the signals and everything to different equipments. So which is why we have a DCS. So DCS is something like a distributed system that monitors different equipments at the same time. All right. So let's take, for example, you are traveling to, let's say let's say from Port Harcourt down to Lagos. Okay. For DCS means we can pass through different routes. It's distributed, so you can pass through different routes to travel down to your location, right? But when talking about PLC, it means you have just one route to get to your location. Now, so it means that for DCS, we can have a lot of equipment, compressors, pumps, towers, a lot of them, and then the DCS is monitoring all of them at the same time. They are sending signals to the controllers do the calculation, send back to the IOs, and then the field instrument in the field, and everything functions in milliseconds, okay? So, yeah, the term distributed system means controlling intelligently, which is spread across several controllers rather than concentrated in a single central unit. Okay, so I think I just explained this. Now, each controller manages a specific process area, such as separator, compressor, utilities, or export system. Now, this architecture significantly improves system reliability and fault tolerance, which is critical in offshore, where immediate system physical access or troubleshooting may be limited due to weather, safety restrictions, or logistics. So if one controller fails, now we have a backup, and they call it redundancy, right? If one pump fails, another pump is there to take over, okay? That's the importance of the DCS system. Now, the failure is going to be isolated, and then another one is going to come back so that the plant does not shut down. So now let's look at the architecture, right? Let's look at the components that are involved in a DCS. So if you look at the image by my left-hand side, you can see the architecture from the systems in the control room down to where we have the panels, and then down to the field where we have the field instrument. So a typical one is something that has the field instruments. I think I have a pen here, so let me just draw this. So here we have the field instrument at the bottom here. So this is a motor. This is an instrument. This is a control valve. Now all these send signal directly to our panels. Now this panel is where we have our controllers. So the controllers are here to do the calculation, optimize, and then send back through what we call the input and output modules. So we have input and output modules. We have the process controllers that are located here at this region. And then we have the communication network, like your feed bus, your cables, okay, that are routed through what you call marshalling cables. So those are passed through here. All these cables are seen. These are cables that send signal to the panel here. Then from the panel, they now send the signal to your CPU at the control room, and then it is now visualized at the monitor, where the control operator is watching everything that is going on, and then trying to optimize to ensure that no accident occur in the plant. Okay, so moving forward, now field instruments are the instruments that measure key process parameters. Now these parameters are like pressure, your temperature, your flow, and also the level, converting physical process conditions into electrical signals. Now what is passing through a pipe is a physical quantity that is passing through the pipe. Now what the instrument is going to do is to measure the physical property of the fluid passing through, and then transmit it into electrical signal down to the control panels, and then the controllers, where calculation is done and then sent back again to the field instruments. Now these signals are transmitted to the DCS through the IO modules, where they are processed by controllers that execute control algorithm at the controllers. Then the logic sequences are carried out, and then interlocks are also done to ensure that maybe, let's say, an instrument is either shut down so that you don't have an accident in your plant. Now, the communication networks form the backbone of the DCS. Communication networks are just like your cables. They're the ones that form the backbone of the DCS. They link the controllers, the servers, and operator stations. Now, in offshore, for offshore DCS networks are designed with redundancy. I think I've talked about this before, to ensure that continuous communication, even if one network part fails. So redundancy means we have two cables, we have two two options so that in case one fails, the other one is sending signal to the field instruments. Now, operator workstations located in the control room provide the graphical user interface. So in the control room, we have two stations. We have the operator workstations, and then we have the engineering workstations. So for the engineering, that is where the control room operator stays to monitor and optimize the parameters, while the engineering part is where let's say any optimization is done. If we want to work on the DCS, want to carry out some optimization like some coding, I think we have some engineers in the house, some DCS engineers in the house. So what they do is they open up the codes and then they try to optimize, try to change at the back end so that you can optimize what is going on. So that's the engineering station. That's where programming is carried out. So DCS versus PLC and SCADA. Now from the image you're seeing here, you can notice that the DCS has a lot of branches, right? So it's communicating with a lot of equipment. And the PLC is just like communicating with one or two equipments, while for SCADA is just like a monitoring unit where you just monitor without carrying out anything. So as you can see, there are no really much of field instruments because all they do is just to monitor what is going on. No control valves, no controllers there. So they just monitor, and then that is it. So when comparing DCS, PLC, and SCADA, it is important to understand their intended applications. DCS optimized for large-scale continuous process, while for PLC, it is meant for discrete controls and commonly used for some package equipment like the compressors. Now, all these equipment, they have their own panel, right? So you can just go there, input what you want to do, and then you put on the equipment. So equipment like a compressor, like the boilers, they have their own panel. Now those panels are PLCs because they are programmed to just function on only that particular equipment. Okay, so that's for PLC. Then for SCADA, they are just for supervising, okay, for just like a pipeline. So the pipeline, you are just there to monitor what is passing through, right? But you are not really controlling what is there. So just to monitor, so that's just it. And, so from an operator perspective, you need to understand the architecture of the DCS. Operator must know where signals originate from. They must know actions to be carried out and how to execute those actions. Okay, so what this means is that if you see something going on the DCS, let's say temperature rising, you need to understand that, okay, this is coming from a social location. There's what they call cause and effect, okay? There's a document from instrument department they call cause and effect matrix. If you have that document, it's going to show you how equipments are linked together, okay? If something happened at the pump, what is the effect? Okay, so that's what they call cause and effect matrix. So as an operator, a control room operator, you need to have that mindset that if something is happening to an equipment, you need to know the cause of what is happening and then the after effect that it will give to the system. So furthermore, let's look at the roles of the DCS in offshore operations. So we are looking at the role of the DCS as in general, not the role of the DCS operator itself. So first of all, we need to know that the DCS, especially in offshore, is a highly required asset, okay? Every offshore platform must have it because without DCS, it means you're going back to analog age, right? And you know, because of the safety implication of offshore platform, everything has to be automated. And to do that, you need a DCS to be able to handle everything that is going on in terms of operation and otherwise. Now, the first thing that the DCS does is to monitor and control. So the DCS is used to monitor and control the operation, right, in general. In the military, they call it command and control. Okay, so that's where they command and then they control what is going on. Now, one of the primary role of the DCS is process monitoring and control. through graphical displays, trends, and status. Okay, now at the DCS, how you can actually properly monitor what is going on is by opening graphs, right? If you open a graph and then you see the trends, you know what is happening, even if you're not on board. And then when you come back, you take over, and then if you open the graph, you can go trace back to as far as a month, and then you try to see what happened based on the graph. If you see a graph that is going up and down, let's say in a sinusoidal wave, you know that there was an issue. So we try to trace what really happened. But if you see a graph that is going smoothly, then you know that, okay, they were having a smooth operation throughout that period. Then we have status indicators. So I think we'll still talk about this later in this training. So for indicators, they show you what is going on and if everything is also smooth. So we also have control loops which are implemented in DCS to maintain variables within defined operating limits by automatically adjusting control valves. So we have what we call the PID. Okay, so the PID is actually at the controller where it enables you to control your operation. So I think we have different kinds of control loops. We have feed forward, feed backward, and then we have cascade, and then auto. So you can put your operation in auto mode. And if your operation is in auto mode, it means the controller will ensure that it controls, the measured variables until it gets to a particular variable, a particular value, and then try to keep it constant at that value. Okay, so that is what the controller does. The control loops is, trying to balance up your operation and ensuring that you optimize it. Now the measured variables, you are the one to impute it. So if you impute, let's say 1,200 kilogram per hour, the controller will ensure that what is passing through that pipe is going to be 1,200 kilogram per hour. So it ensures that everything balances up and then get to that value and then keep it stabilized. As far as the operation is smooth, it's going to be like that, except something, let's say a valve is blocked at the downstream. That's when, it can start, fluctuating again. So that's what the controller does. Now, this automatic regulation reduces operator workload. Okay, so if you are using the controllers and then it's stabilizing everything for you automatically, it means it's going to reduce your work as an operator. So all you need to do is just keep on observing, monitoring, and ensure that everything is okay, because at any time, anything can fail. So even if the controller is doing his work, maintaining that everything is okay, you need to observe, because a personnel in the field can actually go and close the valve, or most of the valves, especially for offshore, they use hydraulic method. So the hydraulic can actually cut off, and then the valve will close. So you still need to continue to monitor what is going on. Now let's look at alarms, interlock, and permissive. So another critical function of the DCS offshore is the management of alarms. Now these alarms these are things that actually help an operator to know if something is going on, right? You can have sound alarm, you can have visual indicators, right? That show you if something is actually off. And then we have colors that, if you see red, you know that the thing is critical. You see yellow, yellow might depend on the company anyway, but yellow might mean that, let's say, there's a faulty connection or something like that, okay? Then if you see normal color, like maybe hash color, you know that indicator is okay. Some can be black, some can be a hash color, then it's okay. But if you see red, you know that something is going on, especially for level. So let's say the level of a tower, and you see red on it, you know that it has gotten either above the set range or below the set range. So you have to do something, either turn off a pump or do something to rectify that issue. Then we have interlocks and permissives. So interlocks and permissives. Now let's go for permissive first. Now permissives they are statements, right? They are statements that actually help or let's say permits an equipment to be put on, right? So take for example for a pump. If you want to power on a pump, there are statements. Those statements, they are at the back end, right? The control room operator is not seeing them, but they are at the back end. That's the work of the DCS engineer. they program it such that this statement must be accepted before an equipment can start running. So I'll use two examples. I'll use the pump and then I'll use the compressors. So for a pump, when can a pump be powered on? First of all, I think it should only be powered on if a personnel in the field goes to the panel to press the on button. Also, it should be turned on if from the control room you press the start button, and sometimes it should be turned on if a personnel from instruments turned on, or let's say electrical turned it on from their panel in their electrical stations. Okay, so that's 3 options. Now the next option is they have oil in the pump that has to be checked. Okay, so if the oil level is low, the pump should not turn on, but if it is normal, then it should turn on. So that's another statement. We can also go for the suction valve. Now, what if the suction valve is closed? Should the pump turn on? That's something you should also consider. So that's also permissive. Now, if the suction valve is open, then the pump can turn on. So another one is the discharge valve, right? In most cases, to make the system more automated, you can also say, okay, if the discharge valve is closed, the pump should not turn on, right? And if it is open, if the discharge valve is open, the pump should not turn on. But if it is closed, or let's say open slightly, then the pump should turn on. So why are the suction and discharge valve very, very important? Now for the suction valve, if it is closed, it means there is no fluid coming to the pump. So if you on the pump, if the pump should turn on, it means there will be cavitation. Because once the pump is running, once the impeller of the pump are running, and then there is nothing entering, it's going to cause cavitation. And at the end of the day, the temperature of the pump will start rising, and it gets to a temperature where the casing of the pump can get damaged. So that is a very good permissive that should be in place. Then for the discharge valve, if the valve is open completely and then you turn on the pump, it's going to affect the pump in a way that the load, right? The load that is given to the pump is going to be too high. So which is why it's good that the discharge valve is closed. It's either closed or open slightly before you turn on the pump. So this can be a permissive. Now, in some DCS, they might not really put this one because they want the field operator to go there and do the lineup, right? So if the field operator does all this lineup and does it perfectly, then they will inform the control operator, okay, we are line up, and then just put on the pump. And that is just to save cost, right? Because the more permissive you put in place, the more money is going to be involved, because you need to put in more instruments and more cabling. You know, a lot of things are going to be involved. So most of the companies, they tend to cut off some of these things just because of money. All right. So for interlock, now interlock, let's say your pump is running, okay? The pump is running, and let's say at the downstream of it, the valve is closed. Do you want your pump to continue running? Now, if the pump is still running, it means the temperature on the line is going to start increasing, right? Now, it will get to a point because the downstream is closed, but then the pump is, taking in fluid and then pushing it through the pipe. Now, if you continue pushing it through the pipe, you see that you get to a point where the pipe cannot withstand the pressure of what is coming in, and then the temperature will start going up. And at the end of the day, before you know it, it will get burst, right? So it's important that you also check the temperature of the line, the temperature of the pump also, so that if there is a valve failure and at the downstream a valve is closed, the pump will just go off. Now that is an interlock. An interlock is telling, okay, something happened, put on the pump, right? So that's interlock for you. Now, anything that does not meet the requirements, if the oil level is too low while the pump is running, shuts down the pump. Okay, so that's interlock. And then I think we've discussed about permissives and interlock currently. So let's look at what we have here. Okay, now, in offshore environments, alarm systems are carefully designed to prioritize safety critical conditions and avoid alarm flooding, which can overwhelm operators during abnormal situations. Operators must understand not only what an alarm means, but also why it exists and what response is required. Now, interlock and permissive form the protective logic layer within the DCS. Interlock automatically prevents unsafe actions, such as starting a pump without sufficient suction pressure or operating a compressor under dangerous condition. Now, permissives define the condition that must be satisfied before equipment can start. Okay, so for permissive is before it can start. For interlock is when the pump is running. If anything happens, it should shut down. So let's understand that. Okay, so offshore interlocks are typically conservative due to the high consequences of failure, and operators must respect these protections rather than attempting to bypass them. So let's look at, I think I said I will give an example for, okay, now let's look at this logic now. So this is interlock and permissives all in one place, okay? Now, if you look at the top, you see, this is for compressor anyway. Now, we have the compressor at this part, and then we have the start, and then we have the shutdown, right? So we have ANDs, and then we have AND and OR, okay? Now, if the loop oil pressure is normal, then what happens? The pump should start. If you look at the flow or the direction of a flow, you see that it gets to the start angle. Now, if the loop oil temperature is normal, it also starts. If the inlet flow, control valve is open, then it starts. If the level of the loop oil in the tank, so you have to look at the level 2, is normal, then start. Now, all these conditions, they have to be in place before the compressor can start. Okay, if any of them fails, the compressor will not start. So these are permissives. Now, if you look at the down parts, now these parts are the interlock. Now, if the pump is running, these are interlock, right? So if the loop oil pressure is too low while the compressor is running, then the compressor is going to shut down. If the temperature of the compressor bearing is, if it is too high, then the compressor is going to shut down. So all these are conditions that states the interlocks and what's it called, the permissives of a compressor.
Sorry, Nati, there is something I observed on that diagram.
Yeah.
That outlet manual valve closed. Is this supposed to be closed or open?
Outlet manual valve. Where did you see that? It's inlet flow control valve. It's open.
On the permissive, I think talking about
on the
permissive.
startup permissive, the permissive outlet manual valve.
Outlet manual valve. Okay, if it is closed.
Is it supposed to be closed or open?
Yeah, this is compressor, so it has to be closed. It has to be closed.
That is while starting the compressor, it has to be closed.
Yes, because you have to build up the pressure of the compressor before you can open the discharge valve.
Yes, that's very correct. So that's why I think no, thank you.
Yeah.
Yeah, that's true. Because whenever we start in compressors, normally it's to take the lube oil out in such a level, and afterwards, before we ramp up the compressor, we have to close that manual valve. It's a valve which it's nearby a spade. That's why this one needs to be closed.
Exactly, because it has to ramp up gradually. So if it is open, then it affects the operation.
Yeah, probably here in our FPSO.
This is not dependent on the kind of compressor.
Yes, exactly. So this is for a centrifugal compressor.
Okay,
yes,
okay.
Yeah.
Yeah. Because for reciprocal, the discharge has to be open.
Yes, that one has to be open. There's no problem with that.
Okay.
For
we can carry on.
Don't have this kind of permissives and interlock for that. It's straightforward. Okay, so we continue. Anthony, please, can you just give us a moment? We'll soon be done with this module, then you can ask a question. Thank you. Okay, so automation of sequence and operating procedures, okay? So like we've seen for the compressor, there are a sequence of procedure that has to be put in place before the equipment can be powered on, okay? Now, as a control operator, again, you have to understand that every activity you're carrying out has procedures, has sequence.
Centrifugal or this something. What forget that? No, there's a name for it. The PD compressor.
Can we?
Okay.
Sorry, sir. Can we write down our questions so that the man can teach when it's done? Then we ask.
Yeah, please. I think that's the best option. Let's write it down. Then we'll okay, so like I was saying, sorry, can we move to our, let's meet, please.
True. I want to take the class. No, 12 to okay, 1 to 3, 1 to 3. We never really miss anything like that. Class start. Maybe they could ask questions 6. No, never.
Okay, so for automation and the sequence of operating procedure, now an operator should know that for you to carry out any activity, there are procedures, there are operating procedures that you need to follow, right? So you don't just start from opening a valve before putting on a pump. Now you need to know the sequence, and then the work of the control operator is actually to guide the field operators in the field to do exactly what you're talking about here, which is setting out the procedure before any activity can be carried out. So DCS also supports automation of sequence and operating procedure. Startup, shutdown, and changeover sequences are often automated in offshore to ensure that consistency, reducing of human error, and minimizing exposure of personnel to hazardous areas. Now, these sequences are designed to follow approved operating philosophy and are rigorously tested during commissioning. Operators must understand the logic behind automated sequence so they can intervene correctly when normal conditions arise. In abnormal and emergency, what's going on here? Right. In abnormal and emergency situations, DCS acts as the operator's primary decision tool. And it provides alarms, trend, diagnostic, and system feedback and guides action. Okay, so I think to summarize this all, the DCS actually helps the operator, to carry out operations by ensuring that they follow operating procedures and sequence. Now that's because if an operator is doing something wrong, the DCS can alert the operator that, okay, you are not supposed to do this. There is going to be an alarm, or let's say a signal that is going to pop out at the DCS, and the operator should know that, okay, something is going wrong. So that is what the DCS can do in terms of automation and operating procedure. Now let's look at the control room philosophy. Now the philosophy is, let's look at the operator now. The operator in offshore is meant to ensure accountability and effective coordination of the entire operation that is going on. The panel operator is responsible for direct interaction. So it interacts directly with the DCS and then monitor process conditions, are responsible for the alarms and then for executing control actions. The field operators, however, they carry out physical tasks, and then they are being instructed by the control room operator. And then also we have a shift supervisor, and it's one that actually coordinates both team, both the field and then the control room. And most likely when there is a situation of abnormal conditions, that's when the supervisor, tries to give out his own experience to ensure that they rectify the situation. Because the shift supervisor is supposed to have a lot of experience. Now, whenever something occurs, he can give a higher observation than the control room operator so that he can easily rectify the issue. Now, shift operations. We all know that in field, both in downstream and upstream, we work in shifts, right? To work 12 hours in and then 12 hours to rest, depending on the company anyway. Some work, I think, 8 hours, some work 12 hours. So imagine sitting down in one chair for about 12 hours. Now that is going to be enormous. It's going to weigh down the operator. So we need to understand that these are challenges that the operators pass through. They give them fatigue, they reduce vigilance. Sometimes operators can slip off due to the long hours they sit down to observe the DCS. And then let's say you are uncomfortable this night, tomorrow you come back again and then you continue. The burden, everything is going to weigh you down. And then the likelihood of errors are going to be there. So the control philosophy, therefore, emphasizes structural shift handovers, clear logging of plant status, and standardized communication practice. Okay, so for control room operators, you need to understand that when there is a shift handover, everything is properly done. You ensure that you hand over the DCS to the next operator by telling him everything that went down through your shifts, the login details, and then also you properly explain everything to the person that is taking over. Now, proper handover is critical to ensure continuity of operations and avoid loss of situational awareness between the two shifts. So errors, human errors. Now, human factors, engineering play a major role in offshore controls design. Now, DCS graphics are designed to be clear, consistent, and intuitive. Okay, so the next module we are going to look at the DCS design. But for this one, let's just know that human factors are interplaying in design, allowing operators to quickly understand plant status. So we'll talk about all this in the next module. So alarm systems are also there. And then it is important you understand that offshore operations are team-based and procedure-driven. Operators are trained to follow approved operating procedures, respect automation systems, and communicate effectively under pressure. Okay, so as a DCS operator, you don't need to be tense whenever there is a situation. You need to calm down and then observe and do what you know best to do. Okay, by giving a very fast response to situations, because that is what you are supposed to know. Like before you get to the control room, definitely you must have been in the field, so you know everything that is going on in the field. Even by closing your eye, you know where your valve is supposed to be situated, right? So if a field operator should tell you that there is a leakage somewhere, you need to know what to do next. You need to inform the field operator to close the valve or do something, or call mechanical team to come down, or something. But it has to be very fast. But then you have to do it without getting tense, without alerting the other people that there is a major crisis going on. A wrong information can cause a lot of chaos in a plant. Okay, so everybody has to be calm, and the field operator is the one that is supposed to calm everybody down and then carry out the activity. Now, many major offshore incidents have been linked to breakdowns in human system interactions rather than equipment failure. Okay, so what this means is that most times it's not like the equipment failure is the cause of some accident that occur, but based on the human interaction, based on the information that is given out, causes panic, and then a lot of things happen. And maybe due to a lack of improper communication and cause accidents. highlighting the importance of strong control, discipline, and DCS competency. So a DCS operator has to be very, very disciplined because your role there is to monitor, carefully monitor. Like there's no time that the DCS operator is supposed to, be relaxed. At all time, you have to be vigilant. I remember a point where we are commissioning a plant. When you're commissioning a plant, the system is not really stable, right? Now at that point, transmitters can be giving you wrong reading. They are not giving you wrong readings anyway, but they are picking out and giving you readings that they are very fast. Before you know, the temperature will get to let's say 200. Before you know, it is down to about 150 and just fluctuating and going up and down. So the DCS operator has to be calm and has to know what to do at that point, right? Now, if it gets to the point where the plant is stable and everything is, very stable, fine. But then you
Hello.
I believe something might be wrong with the teacher's internet. Perhaps soon he will be back. Let's just hold on for a while.
Can anybody hear me?
Yes, I can hear
Yes,
you.
I can hear you.
I'm hearing you.
Can hear you.
Yes, yes, we can.
Oh, sorry, I
We
don't know.
can hear you.
I don't know what happened. I think I lost communication.
Yeah, I believe so.
So sorry, where did you guys hear me? Where was the last part I was talking about? Did I finish? Did you guys hear me when I was talking about the human factors?
Yeah, on the human factor.
Yes,
The human
very
factor.
well.
Due to system interaction.
Okay.
No, you were trying to explain one of your experience about mentioning a plant like that.
Okay. I was saying that during commissioning of a plant, the from the DCS angle, the parameters usually fluctuate, right? They are not really stable. That's because for one, okay, can we mute our audio now? Can we mute, please?
Please, can you share your screen?
Yeah, I'm doing that now. Can you see the screen now?
Yes, please.
Yeah, I can see your screen.
Yes, you can see. You can carry on now.
Okay.
Please go ahead.
Okay, so as I was saying, during commissioning, the plants most likely will not really be stable at that moment. So as a DCS operator, you have to be the one to ensure that you try to stabilize everything. That's because the temperatures, the pressure and everything, they will not be stable at that moment because we have a fluid coming in at the first time. So the transmitters, they have to get used to the fluid that is coming in. So at that moment, everything will be fluctuating. Temperature will be ranging from, let's say, about, for example, temperature can just from 150 come down, fast to about 100, and then before you know it is going up and all the rest. So control operator is the person that actually tries to stabilize and ensure that that commissioning stage is successful, because without the control operator, it's going to be very difficult for that to happen. So basically, I think we're done with our module 1, and then we have questions that we are going to share. So I will share this slide so that you can see the questions that I will answer for this module 1. Okay, so basically we are done for this. I don't know if we need to be taking questions and answers now, or we can just go over to the module 2.
Okay, I have a question, sir, please.
Okay.
Okay, so when you were explaining, you didn't tell us the acronym of PLC and the SCADA. What does it mean? And then my second question is, can we use the DCS to take control? That is it vast? Can you take vast control over PLC and SCADA?
You mean the difference between PLC and SCADA?
PLC, you didn't give us the acronym of PLC and SCADA. And then my second question is, can we use the DCS to control both PLC and the SCADA? Like, can the DCS do what the PLC and the SCADA will do?
Okay. Are you seeing my screen?
Yes, I can see your screen now.
Okay, now this is a DCS, right? The screen you're seeing here is a DCS of a wellhead. But then, if you look at the right-hand side, if you look at the top right-hand side, you see wellhead control panel, right? WHCP. Now, this aspect you're seeing here is this is a panel where all the hydraulics that control the valves, both the downhole safety valves, the subsurface safety valve, all the valves, they are connected to this panel. Now that panel has its own, let's say a PLC anyway. That's the PLC on its own, right? But then it is now tied to the main DCS. Do you understand?
Yeah, I understand.
Okay, now what are the DCS now? Especially for this kind of panel, you are not really controlling it from here. The only thing you are doing is you are monitoring what is going on. So if I close a valve, for example, if I close this subsurface safety valve, you can see the valve here is closed. So from the DCS, you see that it's closed, but you are not closing it from this small panel that you are seeing here, because that panel is a PLC panel. Okay, so it also serves like a SCADA at the panel here, because you're always supervising what is going on. You are not touching it. You are not doing anything there. But from the field where we have the main box, right, you can actually control it from there. You can actually close the valve from there too. So that makes it a PLC at the field angle, but then it is a SCADA on the DCS.
Okay.
Do you understand? So PLC is, I think the acronym for PLC is Programming Logic Controller.
Okay.
So that is just for a small system, like a compressor, like a boiler. If you've seen a boiler before, a boiler has its own panel, has a small panel that you can use to start the burners on the boiler, and then from the control room, you can only see that the boiler is powered on. You can only see the temperature of the boiler, but you cannot operate it. Although they can also program it, depending on the company anyway, they can program it for you to start up the boiler from the control room, but it's most likely not done that way. The field operator has to power on the boiler from the field, but from the DCS, you're seeing everything. You're seeing the variables, the temperature, the pressure of the boiler that is increasing or reducing.
It's very clear now. Thank you very much.
Thank you, sir. Okay. So talking about interlock, right?
Hello.
Talking about interlock, I mentioned that the DCS engineer, those are the people that actually do the background programming at the back, such that if something happened at the upstream or the downstream of an equipment, the equipment should shut down. So let's say for a pump, if let's say at the upstream, which is on the suction side, the valve is closed or is open, something should happen. It's either the pump should shut down or it should remain running. Okay, so let me give an example here now. Let me give an example, although for this one I use the wellhead, right? So take for example, this valve is powered on. So currently I'm lining up. So I line up from the downhole safety valve down to the manifold line, right? And I want to start sending our crude, or let's say our fluid upward. So if I put on sorry, there seems to be an error here. It will not define. Wow. Let's see. Let's use this one, for example. Okay, seems like I'm going to check this programming before we come the next time. There's been an error at the code, so I will check and then I will get back to you. So I just wanted to demonstrate the fact that if a valve, let's say on the manifold, should shut down due to maybe hydraulic failure or something like that, the well is supposed to also shut in, because if you close a valve at the downstream and then we still have the fluid coming up, if it is during a drilling period, we are going to have what you call the blowout preventer is going to shut in and close the wellhead. But during production, it means either the downhole safety valve has to close. Okay, so I wanted to demonstrate it so that you see that. But I have a little program with my code, so I will check it before we come to the next class, and I will explain that. So for the students, I want to ask: do we understand when someone say upstream or downstream? I want the students to respond. The students.
Yes, I think I understand the upstream and downstream.
Okay, so let's take for example, right? We have a choke valve here. We have a choke valve. You see this valve here? So on this valve now, which side is upstream and which side is the downstream?
So which valve is that? Let me try and look at it.
The choke valve here. The choke valve here. Can you see? Let me.
Okay, that's valve there. Okay, this red one. I mean the green one.
This red one. See this one here?
Yes, I've seen it. Yeah. So what is it?
So this is 2 and this is 1. So where is the downstream and where is the upstream?
That valve is
normally when you say downstream or upstream, downstream is I think it's downstream is before also. The upstream is after. Am I right?
The upstream is 1 and the downstream is 2.
Sorry.
Affirmative.
Come back with that. You said the downstream is what?
The one is the
Hello,
upstream.
I hear you.
Yes, I can hear you.
One is upstream.
One is
upstream.
And one is
talking in the
upstream.
background.
2. Yes, 1 is upstream.
Somebody
And
said
2
1
is
somebody said
downstream.
1 is upstream and 2 is downstream.
Yes.
Okay,
Yes.
I want other response.
Affirmative.
I want other response.
1 is upstream, 2 is downstream.
Downstream, yes.
Okay, so everybody's going with that.
Yes, that is it.
Okay.
2 is the downstream equipment. That is the surface facility equipment. Is the
Can
downstream.
you explain what? Okay. So how about this valve here? Look at this valve. XV10 XV10104.
The one to the test header.
This one here. You want to test header,
Actually,
yes.
yeah.
And is downstream.
So this is 1. This is 1. Here is 1. And here is 2.
Affirmative.
So which one is downstream? Which one is upstream? 1 and 2.
One is upstream, then 2 is downstream.
1 is upstream, 2 is
Affirmative.
downstream. Okay, do we agree?
Affirmative.
Yes, I think so. Okay.
Or I can also enhance for the students in a clear way.
This is for the student.
Upstream is where the fluid comes from, and downstream is where the fluid goes to. I think it's should be clear for them.
Okay. Thank you very much for that explanation. So basically, why I asked this question is because During the classes, I'll be mentioning a lot about upstream and downstream. Okay, so if I say upstream of this equipment, downstream of this equipment, so that we know what we are talking about. And like it was just explained, you look at the flow and you can see the arrow here. You see the arrow going this way, right? So for upstream and downstream, you have to look at the flow. You look at the flow and then you know where it's coming from. So upstream is where the flow is coming from. Then the downstream is where the flow is going to, right? So yeah, I believe that is that. So what else? Can we go to our second?
So please, I have a question.
Okay.
Yes, please. Though I joined the meeting quite a little bit late, so I don't know, maybe I'm missing out on something. My question is, how will you differentiate between a SCADA system and a DCS system? Thank you.
Between a SCADA system and a DCS system?
Yes.
Can somebody answer that?
Okay. Let me respond. So a SCADA system, you use it to monitor. Let me use the case of the warehouse.
Okay. No, but we can't hear you again. Okay, someone else should give me the answer. I think.
Hello, sir.
Yes, please go on. I can hear you.
There's some question on the chat box, so I wish you could attend to them. I also sent a question. Thank you.
Hello, Mr. Nati.
The screen is blank. Oh, the screen is blank, please.
Hello, Mr. Nati. I want to throw more light on this, your upstream and downstream.
Okay.
Because from what we understand is from the downhole to the wellhead is the downstream. Then from the choke to the flow station where the crude has been separated from water and gas, then being sent from there to trunk line, TFP, and other floating devices for refinery processing is called midstream. Then from the refinery downward is called the upstream.
Okay. So
no, sir,
okay, so
it's the other way around.
So let me wait. Let me come in. Let me come in there. Okay. Now you are talking about the sectors for the oil and gas, right?
Yes.
So what you mentioned now is you are looking at the flow. So we are getting our crude, or let's say our fluid, crude and gas from the well, right?
Yeah.
So the crude is coming out from the well and going to where? Where the crude is coming
from? Separators.
Or the upstream. Because the flow is coming from the well and then goes to the processing facility, and then from there it can now be sent to by
the refinery
downstream, right?
Yes, sir.
So you see where the flow is coming from. It's coming from the well down to the midstream, and then from there it goes to the downstream. So which is why we are saying the direction of flow is what determines you to have upstream and downstream. That's the direction of flow.
Yes.
So if you're looking at an equipment, you look at where the flow is coming from to that equipment and where the flow is going to from that equipment. Mm-hmm. So the suction side of that equipment is called the upstream, while the discharge side of that equipment is called the downstream. Do you understand?
Okay, sir. Okay.
No, I don't understand.
You don't understand?
This is assumption.
You don't understand? Let's
No, I don't understand.
Okay, let's take for example, let's take for example, this is let's say this is a tower. You can see my drawing, right?
Yes. Yes.
Okay. Then this is the line at the bottom of the tower going to a pump. So this is the pump. And then this is the discharge of the pump going to another, let's say another equipment or tower, right? So from here now, the flow is coming from the tower here, coming down to the pump. Now from the flow here, one here is your upstream, which is why from the offshore, the offshore side is called the upstream because the crude is coming from the offshore and then going to the downstream, right? So from the pump here, we now go down to this other side. So this other angle is called the downstream. So from this pump, just listen, from this pump here, number one is the upstream, number two is the downstream. But for this tower, let's take example. Let's say this, we have the crude coming from another, let's say a separator here. Let's say a separator here. So for this particular distillation tower now, here, number one is your what? The upstream. While here is now the downstream for this tower. So everything has to be based on the equipment. Hope I'm making sense.
Teacher, just please put arrows. Put arrows for them to understand. Put the arrows to show them the direction. So this will be easier for them to understand.
Oh, no, I think she understands. She understands.
Yes, so that they can understand.
Yes, I understand what you're saying.
Okay. All right. So which is why the refinery, the gas plant, they are called the downstream, while the drilling and this other side, they are called the upstream, because the crude is coming from the upstream and then going to downstream. So that is the flow. Okay. Okay, can we move ahead?
Yes, we can move ahead.
Yes, sir, we can move ahead.
Okay, sir. Thank you very much. So,
Sorry, can I ask a question, please?
Okay, sir.
Hello.
I can hear you, sir. Go ahead.
Yeah, I have one question.
Okay, please, I want to know, like, after the this course we are doing, the certificate. How do we get our certificate?
Of course, I'll send it to you. I'll send it to you via either his email or via WhatsApp. Any means.
Okay. That will also know, because very important we get the certificate, because as evidence that we took part in this
Definitely, you get it.
course.
Okay,
right, thank you very much.
Sorry.
But don't forget, you have to meet up. Don't forget, you have to meet up the requirements. Without the requirements, you cannot
Okay,
get it.
no problem. But the requirement, sorry, who's there? The requirement, because I was overheard somebody saying there was an assignment in PDF.
Exactly.
I don't know which of the assignment, because I just joined today. So I don't really know the assignment.
Okay. If you watch, you can just watch the video. Watch the video of yesterday, then you get all the gist from where we talk about.
Okay, I'll get this.
Overview of the course.
Okay.
So I explain everything there.
All right, no problem. Thank you very much. I appreciate it.
For every class, there is assignment that you do, and then you send it as a PDF.
PDF. All right, thank you.
All right. Or Microsoft Word anyway.
Can I say something?
Hello, Mr.
Yes, I sent a question on the chat box. Don't know if you can just attend to it. My environment is noisy.
Hello? Can we move on?
Yes. We'll
yeah, please. Midstream. So you mentioned downstream and upstream. Is there anything like a midstream? What does it stand for?
Midstream is basically, I think somebody said it here already. Midstream is basically transporting it to downstream.
Okay. Just the destination.
Transportation, the marketing aspect and everything from upstream to downstream, in between upstream to downstream. That's the midstream.
Okay, copy that. Thank you very much.
So
All
I
right, sir.
believe the equipment can be referred as the mainstream.
Exactly. For this
from
example,
diagram.
the equipment itself is the mainstream. Yeah, you are correct.
Okay. All right.
Somebody said I should share more light on interlock. I think I've done that already now. Do we need to go back to that?
You can do that if you still have time.
So that please, can we move on after the class? We can revisit back any other questions.
Okay.
Yes.
Okay.
Please let's move on.
Better that way.
Okay.
Sorry, hello, can I just say something? Can I go ahead?
Go ahead, sir.
Okay, some of the instruments you listed in that initial slide, right? I was requesting maybe you list them and the names for those of us who may not come from
Which of the
instrument,
please? Which of the instruments?
And one of the slides you showed the DCS and interconnection with other members, right? Some of us that may not be from process background may not know the name. So yeah, I don't know if you can list them or just to help us learn. Thank you. This slide.
You are talking about this one?
Yes. Yes.
Okay, so what do you want to know there? So we have the field instrument. Now those field
all these instruments, the naming and all that. Just
the field instruments. You know what? See, most of these things after the class, you can just go online, you Google, and then you get some of these things. But the field instrument, those are the instruments that are found on the fields, right? So they are the ones that measure the parameters in the field. For example, we have the control valves, we have the transmitters, which are the pressure, temperature, and flow transmitters. And then we have your pumps. So those are the field instruments and equipment, okay? Then we have cables that connect the field instruments down to the panel. Then also we still have cables connecting down to the DCS again. So that is all these lines you're seeing. These are cables. Some of them are like your optic cables. I think some of them are called Modbus and Fishbus. So just Google online and then you get more details on this. Okay. Okay, so our module 2 now is about the HMI design and process visualization, okay? So here, we just want to look at the HMI itself, and then also the process, how the process is being visualized on the HMI. So that is what we want to look at. So the same thing you are seeing at the on the image you're seeing here. Now, what you're seeing here is called the HMI. Just like on your computer, your screen is called the desktop, right? And on the desktop, you have icons. Those icons are like graphical representation of softwares inside the systems, right? So the same thing happens. The same thing happens on the HMI. So the HMI has can we move our let's see. Okay, so let's continue. So the HMI has a graphical representation of all the equipments on the field. Okay, so what we want to look here is how is the HMI organized, the colors that are used on the HMI, the process indication, and some of the things you need to know as a control room operator or somebody that wants to actually have the knowledge of what is going on the DCS. Okay, so like I said, the HMI is the visual and interactive layer of the DCS. So that is what you see when you sit down on the control room. That's the visual of what you see. And it's representing equipments in the field. Okay, so, and that is where operators monitor, control, and they interpret the behavior of offshore production process. Okay, on the DCS is where it's just like the heart of the plant. Okay, it's like, or let's say it's like the eyes of the plant. Because a field operator will not see what is going on. He's just seeing the tower, the skeleton of the vessels, first stage separator, second stage, third stage, compressors, and all the rest. But he's not seeing what is going on inside. So the field operator, the control operator is who is seeing all those things, the parameters inside. That's the most important thing. Okay, the temperature, the pressure, the flow of what is going on through this equipment. Shaima.
Yes, hello, APD. Thank you very much for this session. I have just one question, and the question is related with the DCS. Please about, because sometimes I hear DCS is drilling control system. Like sometimes you even hear ADCS, that's automated drilling control systems, and I'm seeing here to be distributed control systems. Can you tell me a bit difference about them? And then, is it really related to this, or they are quite the same? Because the other one, it seems is related to the drilling, the telemetry with the semantics and then the syntactics. So with this one, does it really control the drilling, or drilling is not part of this?
No, this one, drilling is not part of it. Okay, the drilling aspect has its own control system. So I think that's what you mean by drilling control system. Okay, so there are two different things. The control operator monitoring production is not the one monitoring the drilling aspects. I think for the drilling, they have a cabin where the operator sits and then monitor the drilling operation that is going on. So that's different from the production aspect, which is for DCS.
So this one, I don't really understand that much. Is it for the rig? Like things that are happening, like not downhole, but above, like above the subsurface, like I'm above downhole. I mean, so this one is only regulating above downhole, not subsurface, right?
This one is regulating production. Now, after drilling, the well is handed over to the operations team. Okay, so drilling is different from production. Drilling a well is production and drilling can be going on simultaneously, especially for fixed platforms. Okay, so while the drilling is going on, we have operators, we have control operators that monitor drilling aspects. Now, when they are done with the drilling, they hand over the well to the production team, and then production team now tie all their subsea equipment to that well, and then they connect it to the DCS. Do you understand?
Okay, yeah, thank you very much. I now understand it.
Okay,
That this one is just for the production,
yeah, this
but
one is
not
for production.
the
Yes.
drilling. Sure. Thank you.
Yes, thank you very much. But then when you talk about DCS, right? For drilling, they also do the same thing. The control operator for drilling also do the same thing. What they do is also to monitor the parameters when drilling, monitor the hydraulic fluid that is going down, monitor the pressure of the well, and try to optimize what is going on. So they are doing almost same thing, but then different systems. Okay.
Sure. Thank you.
All right. So we are talking about operations now. So in offshore operations, we operator manage high integrated systems with limited manpower. The quality of the HMI has direct impact on safety and production performance. Okay, so we are talking about the quality of the HMI now. If the HMI is not actually visualizing the entire plant, then there is going to be a problem. Okay, the operator has to be comfortable to monitor the entire plant, right? So the quality of HMI is very, very important, especially in terms of the color. Okay, so if you use a bright color to design the HMI, it's going to affect the visibility of the operator, right? So, color plays a very important role too. We are going to look at that later. So the purpose of HMI is to support situational awareness, right? So from the HMI, which is your DCS HMI, you can see, you can be aware of what is going on the plant. Now, a well-designed HMI allows operators to quickly understand what is happening, right? So design is very, very important for DCS systems. This is especially important in offshore, where process offsets can escalate rapidly due to confined spaces. Okay. Now, in offshore, you see that equipments are kept in layers, which is why pumps are not even that much in offshore, because first stage, the separator can be on top, while the second one is below. So they just connect a pipe down to this other side because everything is congested, right? So when there is an issue, because of that, limited space, it's very difficult to rectify. So which is why it's important that the HMI is designed in a way that control and automation is done perfectly. So prevents any occurrence. All right, so poorly designed HMI can obscure critical information, delay operator response, and increase the likelihood of human error during abnormal situations. So what are the expectations? What are the expectations for offshore control room? Now, the offshore control room expectations are place additional demands on HMI design compared to onshore. Okay, so what this means is that compared to offshore, because for offshore, the safety requirement is very high for offshore. So because of that, the HMI design for offshore and offshore, they are slightly a bit different, because you have to give more priority of safety to the offshore DCS system, especially since the operator is going to be interacting with the DCS. So you have to make it more friendly, user-friendly to the operators for offshore DCS. Now, offshore operators often work long shifts under high mental workload and must manage multiple process units simultaneously. Okay, so you are not just observing only one unit, you are monitoring several units. You can be monitoring up to 10 to 15 wells at the same time, and also monitoring what is going on at the top side, separators, monitoring the gas compression parts, monitoring the loading and unloading units. So the workload is very, very high. So this means that the HMI must therefore be intuitive, consistent, and free from unnecessary visual cluster. Now, graphics should emphasize process status rather than decorative elements, enabling operators to focus on deviations from normal operation rather than constantly searching for information. So here we are trying to say that on the HMI, we don't need to see, fancy equipment, right? So let's say for a tower, you don't need to put a fancy tower, putting the internals and all the rest. We don't need to see all the internals. What you need to see is just a presentation of the tower, and then we need to see the key parameters that we need to monitor. The temperature at the bottom, at the middle, at the top, at the bottom. You have to monitor all these angles, so you need to put them accordingly. And you have to arrange them so that it is appealing and the operator can easily see and understand what to monitor and control. So this will take us to the design philosophy of the HMI. So the first one is color, right? I think I mentioned about color. Color is very, very important. So if you see, if you look at this DCS, you see the color that is used here. A simple calm color that is not going to affect the eyes, okay? So most people use this kind of harsh color for their design. Some companies use, let's say, a blue color, but a mild blue color, right? And some use black. Mild black color can also be okay. So the color is very, very important. You don't need to put a color that is too sharp for the eyes, because it will affect the operator's visual observation. So color plays a critical role in conveying process status and drawing attention to abnormal conditions. Modern offshore HMI design avoids excess use of brighter colors during normal operation. Instead, neutral colors are used for normal status, while colors while colors is reserved to highlight abnormal alarm or trip conditions. So other colors we can look after is for alarms or trip conditions. So you can use red to indicate, when there is a serious issue, and then you can use color like green. I think green most likely is for when the process is, everything is okay, everything is normal, then we can have green, especially for the write-up. And then we have yellow to show that there is either a connection issue or something like that. And maybe it's blinking to indicate that maybe there's a connection problem. Okay, so this approach ensures that deviations from normal operation stand out clearly, enabling faster operator recognition and response. Okay, so misuse of color, such as using bright color everywhere, can mask critical information and contribute to alarm fatigue. So I think all this, they are very clear. So let's talk about symbols and standardization now. So just like on our PNIDs, okay? Now the symbol used for PNIDs in every country is almost similar due to the code, the ISO code that is used for drawing out your PNIDs. So the same thing for the HMI. When designing your HMI, ensure that you use symbols that are consistent throughout your HMI. So you see a symbol for pump in a particular page. If you go to another page, you are supposed to see that exact symbol. Okay, you are not supposed to be having different symbols of an equipment. So let's say a pump, a pump is always like this, and then you go and then you see another symbol of the pump that is like this. So that creates, it creates confusion for an operator, right? So it's good that we use symbols that, are in line with standard. So equipment such as vessels, pump, compressors, valves, and heat exchangers should be represented using standard symbols that are easily recognizable. So if you go to any DCS a control room, let's say you move from a refinery down to gas plants, down to the offshore. If you see a pump symbol, you should know that this is a pump, okay? Because that is the general standard used for a pump. So you don't need to be using different pumps that are not standardized. So consistency is very important. I think I mentioned that if you use a pump in one page, that same symbol should be a pump in the next page. Okay, so you don't need to change different symbols. Like for heat, let's say heat exchanger now, you can have heat exchanger that's like, let me use the pen. That's like this. Something like this can be a heat exchanger, and then we have the, let's just say like this. Then we have the inlets, we have the outlets, and then we have the, let's say, for the cold side, we have inlets, and then we have outlets. So we can have this as a symbol, but also we can have this circle as a symbol for heat exchanger. So if you are designing your HMI, if you want to use this symbol, then you have to be consistent with using this symbol. So this is inlet, this is outlet, and this is inlet, this is outlet, or this. So if you want to use any of this, it should be the same throughout your your DCS your pages. Okay, so that is what it means here. You have to be consistent with the symbols you're using. So also as an operator, you need to know that they are consistent. So whenever you go to a DCS, always ensure that their symbols are consistent. So once you confirm that they are consistent, then you can be rest assured that they are following the right standard. So in offshore environments, the operators may rotate between different facility or control rooms. Standardization supports faster familiarization and safer operation. So just like we said, you might be asked to move from one offshore platform to another offshore platform, right? So if you are familiar with the symbols of one platform, if you move from a fixed platform to an FPSO, the symbols used in the fixed platform should be the same symbols at the what's it called, the FPSO. They should be the same, or let's say slightly similar. Okay, and that will make you to easily understand what is going on at the FPSO because you already have the understanding. So status, indication, and alarm. Okay, so status indication. Take for example, let's say a separator, right? So a separator, for the level of the separator, we have to maintain a level at a particular level, right? If you get too low, I know we have a pump running. If it gets too low, then it might get to a point where we'll have an empty pipe, okay, and that will cause cavitation. So it means we have to program such that if the level gets to a particular level, there should be an indicator telling the control operator that, okay, your level is getting too low, okay? And then there is a color indicator that always shows that, okay, the level is getting to a particular level. Now, if the operator does not act and the level keeps going down, then another indicator will not show. Let's say a red color will not show. And if the operator does not still act, then what we call a CIS will take over. A CIS is a safety instrumented system that is programmed, that functions without the help of the operator, okay, and that's to safeguard the plant. So all these aspects has indicators that indicate the level of these safety systems. So alarm indication should be integrated into the HMI in a way that supports prioritization and response rather than overwhelming the operator. In offshore facilities where alarm loads can be high during offsets, proper alarm visualization is essential to maintain control and avoid escalation into emergency. Okay, so offshore HMI screen hierarchy. Okay, now if you go to an offshore platform, you will notice that you will not be having just one screen. You might be having as many as 15 to 30 screens. Take for example, you see we have this is screen, this is screen, this is screen. We have different screens here, and I think we have almost 30 screens that are showing here. So what are these screens and what are they meant for? So let's go over to the PowerPoints. All right, so the first one is the overview screen. Okay, there is a particular screen that shows you the overview of the entire plant, just like your PFD and PNID. Now the PNID shows you all the details of everything, piping and instrumentation and everything. But the PFD shows you only the main equipment. So the PFD can be used to make just one screen that whenever you go to, you can see the entire skeleton of the entire plant. Okay, so that is the overview screen. So overview screen provides a high-level representation of the entire offshore facility or major process areas. These screens display key production rates, major equipment, status, critical alarms, and overall plant health indication. The purpose of overview screen is to support situational awareness, allowing operators to quickly identify where attention is required. And then in offshore control room, overview screens are often displayed on large wall-mounted monitors for continuous visibility. As you can see, this control room, we have a very big screen that is showing the overview of the entire plant. And then we have about 4 screens that the operator can bring out different other screens, equipment screens and all the rest, that they can be monitoring, some of the major equipments, but not the entire plant. So that is how the offshore DCS is arranged. Now the next one is the unit operations. So the unit operation is also another screen. Now this one is showing just a particular unit, okay? Showing a unit that has different equipments. So let's take, for example, the separators now. So you have a separator, you have pumps, you have control valves, and then you have, lines and all the rest. So that is unit operations, operation screen. Now these screens provide more details process information, including control loops, operating parameters, and interlocks relevant to that particular unit. Okay, then clear process, flow representation, and logical layout are essential to help operators understand cause and effect relationship. So just like these ones here, this is a unit operation screen. This unit is showing the cool dehydration. So you can see the dehydrator, the valves, the pumps, everything is showing here. So this is a unit screen. And then the next one we have is equipment detail screen. Okay, so take for example your compressor. So your compressor, if you go to some DCS, you see just the box of the compressor as what we have. But then if you click further, or you can have another screen that shows the internal of the entire compressor. So take for example, for this our DCS, let's say we have these are compressors. So you can see these are compressors, right? Now, for me, I just use the box to show the compressor. So we have all our details we need. We have the control valve here. We have your discharge valve and the shutdown valves. And then we have the start button showing here. But then if you click on more details, if you zoom in here, you see more details. So if you click on this compressor details, it will bring out the, oh, we still have a code error. We still have this error that we have not worked on. So, what is this? Okay. So if if you click on this compressor details, it will bring out a different screen that is going to show you the internal of the compressor. Okay, so that is what we mean by equipment detail screen. So that is it. Then the next, I think that's all. I think we are done. 3. Okay, so I think that's all. That's all. Let's look at our questions. So here we have about 4 questions also that we can look at for. So a total of 8 questions is what we're going to be submitting for our day 2. Okay, so I will drop this PDF on the group also so that you can see the questions clearly and then you respond to it. So I think this is the end of today's section. It's been almost 2 hours. Can you guys hear me?
Yes, I'm
Yes, we can hear you.
Yes, we can hear you.
I thought I lost everything.
No.
Okay. So, questions, please. Fango Smart. Fango Smart, you are raising your hand.
Okay, thank you, Mr. Nachi.
Hello, sir.
I joined very late. Please, are we going to be getting the material any moment from now? Yes, I joined late. I have to watch the video again. I came late.
Yes, I will send the video before the end of today.
What about the material?
Yes, I will send the materials too. I used to do that. I will do that.
Okay, sir, I have a question.
Okay, but please, for the materials, please let's not post the entire material on our page. Okay, if you want to post the material, you can just screenshot maybe one part of the material and use it for your posting. But don't post the entire material on your LinkedIn or any platform. Do you understand?
Okay. Yeah. Okay, sir. Sir, I want to ask if, for example, can you hear me, sir?
I can hear you.
Okay. Say one has an experience or a knowledge about, say, onshore, offshore, DCS. Can one switch to the other? Say maybe you're experienced with the onshore processes and the HMI. Can one, if one get an opportunity on an offshore platform, can one still use that experience, the knowledge known on the onshore? Can it be applicable with the offshore?
Yes. Of course, the onshore and the offshore, they're almost same thing. The only difference is that for onshore, you don't have subsea systems. That is the only difference. Every other thing is the same.
Okay, so thank you, sir.
Yes.
Please,
Kamaldeen.
for the last session, we can submit the assessment of the first class as the first assessment anytime. I think.
Sorry, I didn't hear you.
Good afternoon. Can you hear me clearly?
I can hear you.
Yes, I can. I said, can we submit the assessment, the first assessment anytime? Maybe from now till the end of the week.
Yes, you can submit it anytime. From, let's say, but not let's not make it go too long, because every class we have an assignment. So let's not compile everything. But you have your time. Anytime you want to submit, just submit.
Okay, and again, these videos, the recordings, is it only on Facebook, YouTube? We can get it. We can watch it.
Yes, on YouTube.
Hello, sir. Good afternoon, sir.
That means it.
Although later I will upload these videos on my website. But I believe by a month's time, the website will be on. It will be live. For now, we are still programming the website. So.
Okay.
Hello, sir. Can you hear me?
Yes, I can hear you, sir.
Mr. Lati, okay, my question is that thank you for the presentation. So
okay,
my own question is that DCS shows the different equipment out on the field. So, and I discovered that you've not walked us through how these equipment are routed from the field to the control room. And then before we can be seeing each instrument on the screen, how are they configured? There should be a configuration that make them appear on the screen. And then if any button is clicked to make them respond, how are they interconnected together? Can you walk us through that, sir?
Okay, if I can help on this one.
Okay, go ahead.
Please, can I help on this one?
Yeah, go ahead.
Okay, so basically, this course is just telling you an overview. The configuration and of this one is purely design. Okay.
Exactly.
But as an operator, you have to understand the philosophy. Okay, the DCS operating philosophy. So if we talk about level control, there's a philosophy around level control. If we talk about pressure control, there's a philosophy. So the design itself, the person who is designing the whole thing has an operating philosophy. Okay. So let's say we have a separator. A separator, there's a design philosophy, control philosophy around the separator. So as an DCS operator, you have to know this philosophy. So whenever there is a compressor, you are sitting down and you are able to identify this is a positive displacement compressor or a centrifugal compressor. The control philosophy is there. That is your tool as an operator, the control philosophy when you are on the DCS. Because interface must change depending on companies. But whenever you find yourself, it is the control philosophy which is the tool that you use to attack or use to operate the interface. Okay, so talking about configuration, talking about these things, and we are basically taking a training of operator. It's purely design. Okay.
Okay, thank you very much. So I think that's exactly what I wanted to inform him.
Hello, Mr. Nati.
Yes.
Hello, Mr. Nati. I want to say a very big thank you for your lecture.
Okay. Let me just sorry, you will come in. Let me just add to what this person was explaining. Okay. So, like he said, what we are here for is the operational angle of the DCS, not the design or the programming angle. I think if you want to learn that aspect, then you need to go for a DCS engineering class, right? But this is an operation class. So we cannot go back to how it is, the backend is being programmed for everything to function. But what we can do is, while we are going through while we are going through all the equipments, what you need to understand is how that equipment is functioning. Like when we get to something like a heat exchanger now, what is going on inside the heat exchanger? How is it configured? How is the cold side and the hot side being configured? And what is the interaction going on? That is what I will explain when it gets to this angle. Okay, the operational angle or operational aspect of the equipment, I will do that. I'll explain to you why a valve should be closed, why it should be open. Get what makes temperature to go up, what makes it to come down. I will explain that. In terms of all the equipment, when it gets to compressors, I will explain. When it gets to the hydrator units, I will explain both the equipment. I will be telling you how everything is done, but not the programming aspect. Do you understand?
Hello, Mr. Nat.
Yes.
This is Michael. Michael. Noga.
Okay. Okay.
Okay, please. I saw payment about 30,000 naira payment. I don't know. The payment is it for the certificate? I don't know what the payment is for. Like,
It's for the
you just let
certificate.
us know.
It's for the certificate.
Okay, so we send to the account that is there.
Yes. We have different options there. If you happen to be in Nigeria, you can just transfer to the account in Nigeria. If you're in Ghana, if you are in other part of Africa, then you can go to your bank and then tell them you want to do interbank transfer. You understand?
Okay.
So that's that.
Hello,
Alright.
Mr. Nati.
Yes.
Okay, thank you.
Yes.
I want to ask.
My name is Fidelis Soje. I want to say a very big thank you for this class. What I want to say is that most of our universities, they should inculcate practical classes like this into their learning instead of theoretical teaching of just drawing a separator and this and that. Because from your teaching is someone who attended the university for 3 to 4 years. From what I'm seeing on your screen like this, I think people like you who are educators can inculcate into the system of the university so that most of our undergraduates can be well grounded in all these systems. Even graduates. Some of them have never seen crude oil before. They don't even know what is a separator, whether it's a vertical, horizontal. These are the things we are lacking in the field.
Exactly.
All right, so to me, please, I want to ask, how recognized is your certificate? Is it ISA compliant?
Sorry, who is talking, please?
My name is Ubonga Basakwabi.
Okay, your voice is cracking. Please, every other person should just mute their mic so that everybody this person can talk. Obonga Basi, right?
Good day, sir.
Right.
Please, I want to find out how recognized is your certificate? Certification, yeah. Does it have the ISA compliance?
I can't hear you.
He has a radio on.
Is asking if the certificate is recognized, if it's ISO recognized.
Okay, ISO. No. We've not linked up with the ISO yet.
Okay, sir. I want to ask. Can you hear me, sir?
Yes, I can hear you.
Okay. The DCS, are they built specifically to suit a particular feed or equipment? Say, for example, from this DCS that was built by you, was it built specifically to suit a particular feed, or someone else can also build something to work to perform the same operation as this DCS on that particular feed, or there's a standard that was built that every other plant or every other feed can just inculcate inside their own DCS?
Okay, the standard is meant for just like we mentioned there, the symbols, and then maybe the colors and all the rest. Those are the ones that are standard. But in terms of the programming, it is programmed based on a particular plant, particular equipment. So you can't carry the DCS of one plant and take it to another plant and it will function, because most times they look at most of the things you have to calculate, even the density of what is passing through.
Okay.
Yeah, so you can't use the DCS for a refinery to work on the DCS of a gas plant, because the fluid passing through, they have different densities and boiling points.
Okay, sir. Thank you.
Okay, sir. Okay, so I think we can stop here for today.
Thank you very much, sir. Thank you.
All right. See you guys on Wednesday.
Thank you, Mr.
Yes,
Nati.
sir.
All right. Have a lovely day.
Mr. Nati.
Isaiah. Well done, sir. Okay.
Okay, see you.
Mr.
Thank you, Engineer Nati.
All right, thank you
Engineer
very much.
Nati, thank you very much.
Thank you very much. See you guys.
Thank you very much, Engineer Nati. I really appreciate this
Thank you,
course.
Michael.
It's a very good one. Yeah, very good one. Very good one.
All right, sir.
Thank you.
Thank you, Leonardo. Thank you.
All right. What's with Carlo? Thank you for joining.
Yeah, thank you.
Manuel Effiong, thank you. Friday. Thank you.
Yeah.
Engineer Otiso.
Thank you, boss.
Ubong Oyo. Eyo. Thank you. All right, so I'm going to end the live now.